Hello, today we're doing an ANSYS Fluent project. My name is Pete, and we first start out by opening up ANSYS. So we go ANSYS. We're going to open up Workbench within ANSYS. And we will be doing COUETTE hybrid Poiseuille flow through a pipe. And the flow is going to be laminar. So we're opening up the Workbench within ANSYS Fluent, or ANSYS. Okay, this is the Workbench, and we have to go to Fluid Flow Fluent. Click on it and drag to the green box to start a new project. We left click geometry, use a new design modeler, in the bottom left hand corner it says it's starting the modeler. Alright, we're in there. Click XY, double click Z. We're going to draw in sketching, draw a rectangle at the origin. Go to dimensions, the height dimension, select horizontal for the length dimension. We'll set our units to millimeter. The the length is going to be 500 millimeters. The height is going to be 10 millimeters. Then we go, well, let's zoom in on this a little bit so you can see the object. It's a pipe, 500 millimeters long. We go to concept, surfaces and sketches. We click apply, we select edge. Click apply and generate. Now we have a pipe. As I make this a little bigger, I'll try to drag it towards the center. All right, there we go. All right, let's close this out and go to meshing. All right, double click mesh. Just checking my notes real quick. I'm gonna refer to them every once in a while. All right, we're in the mesh section. We're gonna double click. Well, let's wait for it to load. All right, double click on the Z. You zoom out a little bit. we're going to right click on mesh, insert, method. We're going to click on the object, geometry, apply, and generate. Just divide up the pipe initially into quadrilaterals. On the bottom left hand corner, it tells you how far it is along with the meshing. Did it pretty quickly, so it says ready. But that's what that first meshing process does. We're going to mesh it a few more times. So we're going to go to right click, mesh, insert, sizing this time. We're going to make sure this is on edge. We're going to select the inlet edge, hold down Control, and the outlet edge. Let go of Control. Now apply, shows two edges that were selected. Element size is going to be, change the number of divisions, 100 divisions. We're going to capture curvature. We're going to scroll to no. And for soft, we're going to change behavior to hard. Generate. Lower left hand corner tells you the progress for the meshing. Let's click on mesh to see what it did. You see it made like a alligator type of turtle design. We're still going to do some more meshing. So we're going to go to mesh, right click, insert, sizing. We are going to select the top wall. We have edge on the top selected. So we click top, Control, hold down Control, click the bottom wall. Let go of Control. Apply. Element size is going to be number of divisions, not element size. Number of divisions, let's say 500 or 500 millimeters. Click Enter. Capture curvature, make it no. Behavior, make it hard. And then we're going to generate. Progress is in the lower left. It's running a little slow lately. Meshing usually takes a while, but today it was running kind of fast. I don't know why it's going slow. It's probably tired. All right, so let's look at mesh and see what it did. So now it's black. It looks like a solid, but if you zoom in, you'll notice that it's subdivided into little elements. Now we're going to mesh one more time. We'll go to face meshing. We're going to just click the body this time. Apply. Don't change anything. Generate. Progress is in the lower left. All right, finished. Click a mesh to see and zoom in, see what's going on. Notice they made even smaller rectangles and divide things up even more. You need meshing done very fine in order for the computer to generate, or the program to generate, accurate results. The smaller the meshing and the more elements you have, the more accurate your results are going to be. So one last thing, make sure we're on the edge. Name our edges. So click one edge, type N for name, I'll name it upper wall. Do the same thing for the bottom. And lower wall. Inlet. And type inlet. I'll click the outlet. And outlet. You can see if you did it correctly. Expand name selections. Click on upper wall. Shows you where you clicked. Lower, inlet, outlet. Now we'll close out the section. That ends the meshing section. We go ahead, we update mesh. Right click and select update. All right, it updated mesh. Now we double click setup. This is pretty quick. All we have to do is change the solver to double position, make sure dimensions on 2D, and start. Wait for that green check mark, or for it to open up, should I say. Takes a little bit for it to load. After it loads, we can press OK or check out of that little small box in the center. There's a console at the bottom of the screen, and it shows you that it's processing whatever processes it is doing, whether it's iterations or something else. There's an hourglass. It shows you it's still running. Wait for the hourglass to stop. It looks like it has, which is a good sign. So let's go to general. We're doing COUETTE-POISEUILLE today. I'm going to try to do it right off the bat. So general, we check we want pressure-based solver. We want velocity formulation. That's absolute. 2D space planar and time steady. Go to models. Going to change it to laminar. Okay. So we change what was before. It was a viscous SSD, and we changed it to laminar. All right. So materials, make sure it's fluid, air, density 1, keep it simple, 1e to the -5 for viscosity. Change create, close. Check cell zone conditions, fluid. Should be air. Apply, close. This is what the boundary conditions, which changes the cases. We want the inlet. We want a velocity of 5 meters per second. Apply, close. Outlet, should be pressure based. Yes, just leave it at that, 0 gauge pressure. We want the lower wall to be stationary and upper wall to be at 3 meters per second in a positive X direction. That's lower wall, we want it stationary. It's fine. No slip. Apply and close. Upper wall, want 3 meters per second. So we click on upper wall, wait for it to open. We want to select moving wall and speed 3 meters per second. Apply, close. Let me just double check that. Upper wall 3. I'm going to check it anyway somewhere else. Okay. Well, I'm not sure we will show up in there. Anyway, I'm going to go to reference values, which usually where you can check your values that you've entered previously. We're computing from the inlet, so you're going to select inlet. Area is 1, density is 1, depth is 1, 0 gauge pressure, 1 e to -5, inlet velocity is 5 meters per second. So specific heat ratio is 1.4. It looks good. So we have to initialize. Let me just make sure or something. Something called residuals. That the smaller the residuals are, the more accurate your results are going to be. 0.001, I'm going to leave it at that. Initialization. Hybrid initialization. I'm going to change it from 10 iterations to 25. And I'm going to initialize. And in the console window, you'll see it initializing. Stops at 25. All right, initialization's done. We'll go to calculation now. Run calculation. I'm going to put iterations 500. Everything else should stay the same. And calculate. Let me check my notes while it's calculating. In the windows, you see the residuals. And the iterations in the console window. Just because you put 500 or whatever number for number of iterations This doesn't necessarily mean it'll take that many iterations to finish the computations. Such as now, it didn't use all 500. So calculation is complete. We're going to generate a velocity vector. So we go to result at the top, go to vectors, new, we'll name it velocity vector. Or vectors. So we'll show when we generate the chart. We're going to select all of these. Everything else is good. Compute, save, display. So it was pretty quick. Looks like it didn't do anything. But if you go with your mouse pad or your scroll wheel on your PC, you zoom in, you get the image. So remember, this is hybrid Poiseuille-COUETTE flow. So we can move this out of the way, the legend, and bring it to the top. Just click on it, hold it, and drag to the top. Let me see. Yeah, hopefully this moves out of here. I don't like it. But it shows you the progression of velocity going from lower velocity, gets darker along the length. That means the velocity is increasing. Lower velocity at the inlet and increases to higher velocity at the outlet. I'm going to zoom in so you can see the velocity vectors. So you zoom in, and we went real small, so I have to zoom in a lot. You can see the arrows, and those are the velocity vectors at that level in the pipe. We have boundary layer prominent at the bottom, and we have also some boundary layer at the top. And we have development in between both of those boundary layers. And it's an asymmetric development. Let's see something. Let me just look at my notes. All right. So we're going to go back to results. See if I can X out here. Okay. I'm going to go back to Workbench. All right, double click results. All right, update. It's telling me update, so I'll update. All right, double click results. Okay, wait for it to load. Double click Z. I'm gonna have to go back and forth. All right, we're gonna name the midpoint and endpoint. We create midpoints and endpoints. So we go location, line. I'm gonna name it midpoint. Okay. The midpoint, it's 500 milliliters, so I'm gonna, in meters, it's 0.25 meters from each way to the midpoint. And then the height is 10, sorry, this should be 0.25. Height is 10 millimeters, 0.01. Let me just double check my notes. I'm going to select, put the iterations to 100, or samples to 100. All right, let me see if everything else is good. I'll take out the 0. All right, I'm gonna let me see, do the endpoint next. Let me just get my notes in order. That's not what I want to do. All right, click location again and create an endpoint. Location, and then we're gonna name it line. It was line, and we're gonna name it endpoint. The length is 500 millimeters. I'm gonna go slightly before the end, 0.499. I'll leave it at 3 nines. 0.01 for the height again. 100 samples. Let me just make sure. Look at my notes. Now click apply. Did I forget something? Let me just double check. I don't think I did, but I had to check anyway. You click apply again. Make sure everything's okay. Let me try this process again. Let me see if I can delete this and start this again. So, location, line, type midpoint. Okay. 0.249. I'll just put 0.25. And for this, I'll do 0.01. And click apply. And you'll see that yellow line at the midpoint of the pipe. I'm going to go to location again, clear the line. I'm going to create endpoint. Okay. You see that's adding here, which I didn't see before. We're almost to the end, but not exactly at the end. So we're going to 499.9 millimeters of the length. your samples, and apply. And it should be a yellow line at the end. I'm gonna delete that. Let me see if I can just change this. So 4995, because I'm not seeing it. So now I see it very lightly, but there's a yellow line right there. That's the end point. All right, good. All right. So let me check my notes. I'm gonna go to the contour square, and we're gonna get a generated velocity map. So the contour square is up here. Click that. We're velocity contour, I believe. Yeah. Let me just make sure that's what we're doing. Yep. Okay. Location, symmetry 1, variable, velocity u. Let me just make sure. Look at my notes. We're going to do 100 iterations or 100 contours. All right, let me go back. Where is this? Let me go back to this. Velocity contour. I didn't apply it. I think that was the issue. All right, let me do it again. It's going to be symmetry 1, I believe. Symmetry 1, variable, velocity u. I don't have to do anything with that. I shouldn't have to do anything here. No. I'm going to press, or go back to geometry, press apply. Why? That's not what I want. I don't think. Okay, so I think you can do it a different way. I go to results. Well, before I go, See if I can do a profile chart. Let me go to chart. Velocity profile, name it. Title, velocity profile. XY line is what we want. We're gonna define this series 1 as midpoint. XY axis. Let me just see. Location. Midpoint. Variable is going to be velocity u. Velocity u right here. Y-axis. Let's see. Do I have everything here? Why is this not? Oh, let me add on. Sorry. Then I'm going to add on endpoint. Location. Wait. All right. Location. Endpoint. The excess velocity u. Y-axis is going to be y. Press apply. Let me check my notes. Click apply. And those are the velocity profiles of endpoint and the midpoint. The velocity at the midpoint, which is red, has not yet achieved the same profile as the velocity profile at the endpoint. So it's still developing. The blue is the endpoint, red is the midpoint. Velocity profiles. All right, let's see what we have. I need just 1 second. So let's see what else we need. I'm trying to skip over doing individually COUETTE, and I'm trying to go straight to the hybrid. So here. We're on chart viewer. Let's see 3D viewer. That's what the velocity contour is supposed to be, but I'm going to try to go back out of this. Let me go back into solution. Because I think we could have done things in here. Wait for it to load. It usually takes a little bit to load. Let me go in, look at the numbers real quick, and I'll start generating some more contours and things like that, the way I know how to do it. All right, let me run through this real quick. General. Yep, that's good. Models. Viscous laminar. Materials. Fluid, air. Okay, looks good. Cell zone. Fluid. Boundary conditions. So you want the free stream velocity at 5 meters per second, which it is. Let's look at the outlet. It should be pressure outlet. Prevent reverse flow. That would have been nice to do. All right. Just double check them. Walls. Bottom wall should be stationary, and the top wall should be a velocity of 3 meters per second in the positive x direction. So let's just check, see if the lower is going to be stationary. It is. Upper 3 meters per second. Okay. All right. I think. All right. I'll check these. Check the reference values. So double check inlet. These look good. I'm gonna uncheck that. Initialization and initialize. I could have gone the wrong calculation and done initializing wrong calculation, or I'd rather do them individually. Maybe I should do it that way, but I'm doing it separate. So I'm going to go to wrong calculation. All right, I'll keep that as before. Press calculate. Hopefully it doesn't freeze on me. Does take a while for it to compute. Probably my computer's very tired as well. All right. Let's see. It's generating things. Let's go to graphics. Go to contours. I'm going to generate a velocity contour. I did it with vectors before. I'm just assuming velocity now. Select all these. Compute. Generate. Or save display. And that's a velocity contour. Try to move this out of the way. Let me just close that. And let me zoom in a little. I'll zoom in even more. Move this out of the way. Click on it and drag to the top. So velocity contour shows lighter orange to deeper red. So it's going from a lower velocity to a higher velocity. Velocity is increasing along the length of the pipe. I'm going to zoom in a little, and you should be able to see from the inlet. I'll get back out here. We should be able to see there's no boundary layer, and the boundary layer is increasing along the bottom length to the end, and it's also doing it at the top as well on the moving plate. So if I go to the end of the plate, you'll see that lower wall, the boundary layer is increasing in height as it traverses along. Let me generate another contour. Pressure contour. Select them all. Compute. Display. Move this out of the way. And as you see, and as I hopefully can get on the screen, all right? So high pressure at the beginning, zero velocity. So velocity increases, the pressure is decreasing. So your max velocity is out at the end, and you have max velocity, and that means the minimum pressure. If there's anything else here, let's see, velocity. Okay, let's close this. Let's see, did vectors before, plots. We did it before. Let's see. I want to see the forces. So I have the drag force in the x direction, the direction of the flow. If I just do it along, actually I don't have to do it for this part, so I'm not going to do it. Let me just double check. We did velocity contours, we did vectors, the velocity profile before the midpoint. Pressure gradient. Do I still have the, yeah, sorry. So the pressure gradient, like I said, is going from high pressure to low pressure. So from the inlet, high pressure gradient, and to low at the end point. So it's a favorable pressure gradient, and it's being illustrated on the graph from the red to the blue, from high pressure to low pressure, which is a negative pressure gradient, and it agrees with the theory. Okay. Let's see what else we need. Close. See if I can go up here. I already did those. I already did the XY plot and it showed the midline and the endpoint. And at the endpoint, at the middle Y height, what is showing was the maximum velocity because it was fully developed. All I can do here. So I would have to go back, but I don't think I can. Let me see something. So all right, it's still here. Velocity contour. I'm gonna go to chart view. Is it there? Oh. Velocity profile. That's what I'm looking for. So this is hybrid. This is COUETTE-POISEUILLE. So it's not symmetric on the velocity profile. You have the development, full developed, or at the endpoint. At the midpoint, this is the velocity profile. So this is working towards the endpoint. So this is the point of fully development. It's still developing here. It hasn't gotten to the end. At maximum velocity, it's going to be approximately a little over 6 meters per second. You're getting the free stream plus the moving plate on the top. Combined together and working against viscosity, you're getting a little over 6 meters per second. It's occurring at approximately at a Y height of 0.005 meters. Or 5 millimeters. So the total height was 10 millimeters. As you see 0.01 at the top, 0 to 0.01. So at 5 millimeters, that's where actually, you're not getting as much of a parabola because you're getting more uniform development in both cases, midpoint and endpoint. So it's harder to tell where the max. Let's say it might be up here. You probably have a flat area. It's all becoming more uniform due to the nature of the COUETTE-POISEUILLE flow. Anyway, it's approximately somewhat in between top and bottom plate, almost symmetrically, let's say. But you can count it as maybe slightly higher. So maybe it's a little 5.5 millimeters, possibly that would be where you have max velocity. And that answers that question. Let's see, is there anything else? Max velocity, pressure gradient, talked about the velocity profile, pressure contours. So I think that's about it for this video. Hope you enjoyed it. Sorry it was a little long, but I tried to go through it. Thank you so much, and have a good day.